Good evening and welcome back to Vegas October 1 Sounds. Uh, this evening's topic of discussion is lrad Part 2. Basically, this is a continuation of the discussion I had last night about lrad. And I think people have great misconceptions and don't even know what they're talking about when they say lrad. lrad is a generic term, and actually, if it's in all uppercase, it's a copyright term. And it stands roughly for Long Range Acoustic Device. And the company that makes the all capital copyright device or devices has several devices with several parameters, several frequency responses, several power outputs for several different applications. So just using the term lrad is a big disservice to anybody who wants to demonstrate a theory of how sounds were generated that night. So let's start back at the basics, and maybe a little bit before that. The history of what we call parametric speakers, which is a generic term, and you can Google it, to describe the type of devices used that broadcast sound in a way that it can be heard in a much narrower region than the traditional voice coil speakers that we're all familiar with from our audiophile systems. And the general characteristics of these types of devices are that only one or narrow region of space can hear the intended message. And there are indoor versions, there are outdoor versions, there are high power versions, there are low power versions, there's wide angle versions, low angle versions, low frequency response. Some of these devices only broadcast in a very narrow band of frequencies that is audible. In fact, there's a big group of them that broadcast from 2800 hertz to 3000 hertz. And the normal range for just voices is somewhere from 1 to 3 kilohertz. None of them, that I know of anyway, are audiophile quality devices. That is, none of them will faithfully reproduce what you might even hear on a CD. And there's a lot of reasons for that. All of them are line of sight. That is, if you don't have a clear view from your device to your intended target, then the target's never going to hear that. And that's a function of the way that these things operate. And there's several different implementations of these types of devices. Some use microwaves, some use sound, and some use entirely other means of achieving their intended result. But we're going to focus mostly on the sounds. And within those that use sound as their medium, there are two different types. And I'm going to focus only on one because it pretty much demonstrates everything we need to know about all of the others. And this is the one type that uses self-demodulating signals. And what happens here is that they use a series of little bitty piezoelectric devices acting as regular speakers, and they put them in a group and they manipulate them with high-powered electronics such that they can create a narrow beam of focused high-frequency sound. And that high-frequency sound is above the frequency at which we hear. Our hearing stops, oftentimes well below 20 kilohertz. So as these devices choose 33 kilohertz and, sometimes up in the 100 kilohertz frequency to carry their signal. And then what they do is they vary that frequency they fix a point, let's say they fix a point for the carrier signal of 100 kilohertz, and then they vary it by a few frequencies, so from 110 to 120 kilohertz, and when that signal, which you can't hear, hits this object or a surface, it basically self-demodulates, eliminates the 100 kilohertz, and all you'll hear is the 20 to 20 kilohertz signal. So, but line of sight. What does line of sight mean? Line of sight means that if you stick something in front of the signal, you won't hear it. And you won't hear it because these high frequency signals don't refract around objects that are very large. They refract around objects that are very small, but everything in the real world, relative to the signal size of the sound that they're using, is large. So if a person is standing in front of you and you're standing behind them, and the lrad signal hits them, you won't hear a damn thing. Or if you're behind a wall, you won't hear anything. That's not precisely true. I mean, when the signal hits a wall and it demodulates itself and becomes audible, the wall may in fact reflect some of that sound towards you. Then again, if you're behind the wall on the opposite side, you won't hear a thing. Unlike traditional sound, which is in the for our hearing, to 20 hertz to 10 kilohertz or above, the low frequency stuff will bend around things. The muzzle blast, for example, being often less than a kilohertz in frequency, will bend around corners, they'll bend over walls and everything. The higher frequency sounds don't bend as much because as the wavelength shrinks, the ability to refract around objects of any substantial size is reduced. And that's why things like radio waves and microwaves and high frequency sound waves all are line of sight things. But the lrad has these lrad devices, as they're called, have the additional problem is of this demodulating. And the minute they hit something, they demodulate. And you hear the audible sound, but then the carrier wave is gone. And without that carrier wave, there's no way for the next target object to hear or get the effect of demodulation. So if you're hidden under the stage and you hear gunshot sounds, then they most certainly did not come from an LRAD device, because you don't have line of sight. Now, maybe the LRAD signal hit the stage, and you can hear a little bit of the gunshot sounds because it's kind of vibrating the wood or whatever the stage is plywood made of, and you can hear that, but you won't hear this very prominent thing. The other thing is that given that each LRAD device has a limited frequency range that it broadcasts in, you won't hear the full frequency spectrum. And the general frequency response for a muzzle blast is on the order of 20 hertz to let's say about 600 or maybe even 700 hertz. Well, if the LRAD device can only go down to 1 kilohertz or 1000 hertz, then it can't recreate the muzzle blast. So these are very big limitations that make the use of LRAD devices essentially impractical for the recreation of gunshot sounds, and certainly in a way that's faithful to the physical phenomena. So let's draw a few graphs and make what I just said a little bit more explicit, and then I'll continue this discussion to talk about some more of the interesting phenomena that we associate with these devices. So, in a typical LRAD device that we're talking about, the one that these parametric speaker systems, as they're called, we have a bunch of little bitty piezoelectric speakers, and in some of these they're arranged in a grid, and they can all be operated independently. And these devices since they can be operated independently, we can program them to do anything at any signal strength at any phase. So this one, for example, may be oscillating at 1000 hertz, and the next one on the inside over here may be operating at 150 hertz. So they're all independent. But if you put them all very close together and they all broadcast the same signal, then their sound is additive. That is, there's constructive interference going on, and that makes the overall sound louder. But just like a normal speaker, if we do that, then the sound, and over here let's draw the side view of it, then the sound coming from the device would radiate like a normal speaker, kind of off at an angle, and you would have no control over it. So what happens is the LRAD devices, they choose these exterior, and this is just one possible implementation. They use these exterior ones and they operate them at a slightly different frequency, and it doesn't do constructive interference. It does both destructive interference, and because of the way they can do the phase of it, it'll cause refraction. We'll just talk about destructive interference first. So destructive interference basically eliminates or reduces the sound of the things, say, up in this range, and similarly on the other side, it would reduce the volume of these things. Now that's just a pure waste of energy, but the net effect is that the beam size of the signal is reduced. That's one way of doing it. Now the other phenomena is refraction. And what they do is they oscillate these speakers, particularly the exterior ones, in a way which causes a reflective surface. And I'll draw that back up there. So instead of having this normal sound radiating out, you get a reflective surface, something like that, which keeps everything in, no matter which way it's going. It kind of bends all this stuff in, similarly on the bottom. And that's a crude, representation of what's really going on. And so you don't get that vast spreading associated with just normal broadcasting of coherent sound. So that's essentially the way that these types of LRAD devices work. Now, they in terms of how they keep the beam narrow, and since you have all of these little bitty piezoelectric devices under programmable control, you can do anything you want with them. So in fact, you can actually make it a wide signal, not quite 180 degrees, but probably 160 degrees. So from one LRAD device, you could program it to do a little narrow beam, the width of the device, or you could change it to be 5 degrees wider than that, 10 degrees, 20 degrees, 30 degrees, 160 degrees wider. Now the wider it goes, the more the total energy of the device is spread, and therefore the less the volume of the sound that gets heard, and therefore it reduces the effective range of the device. And so when you have these LRAD devices that narrow the beam down considerably, then you get essentially more power, a narrowly focused beam of higher power stuff. Now let's take this beam. It operates at, let's just pick one, 100 kilohertz. 100,000 hertz. So this beam in here is oscillating back and forth at without any input of 100,000 hertz. That's way above the hearing. So no matter what happens, this signal would not be heard if it hits you. Just nothing. You hear nothing. Some things might feel that signal because they have a resonant frequency associated with 100 kilohertz. Most things in our body don't have a resonant frequency near there. So then what we do is we on top of that signal, you bring something in from, let's say, an MP3, which has a frequency range of approximately 20 hertz to, let's say, 10 kilohertz. And you lay it on top of this in a way that causes this signal to not just be 100 hertz, but have all little bitty things on them in a way that's very unique. And I'm not going to go into the technicalities, but it's extremely complex and mathematically involved. So anyway, you now have this stuff that was on the MP3 and the audio range layered on top of this 100 hertz signal, and because of that, the MP3 stuff is raised from 20 hertz to 10 kilohertz to 100,020 hertz to 100,010 kilohertz, 100,000 and 10,000. So it's still above the audio frequency range, but then when it intercepts an object, When this beam intercepts the object, it hits it, and in the process of reflecting back, it interacts with itself, and the 100,000 hertz cancel out, leaving just once again the 20 to 10 kilohertz. And that's how we get the audible sound. So, knowing that, then, let's draw another picture. And remember, this is just one type of implementation. They all work slightly differently. So if I've got a device, and typically these things are elevated or up here, let's say, and it's got a beam and it's transmitting down somewhere. Okay, let's say it hits that leaf there. Then anything in what we call the shadow of that leaf doesn't hear anything. And so if you have an lrad device and it broadcasts out a beam and it hits a wall, then anything in the shadow over here doesn't hear it. Similarly, if you have an lrad device and it's broadcasting a beam, it hits a person and that person hears it, then anything in the shadow doesn't hear that. So an lrad device really is a very limited device in terms of reaching mass fields, unless it's done at an elevated location and it points essentially down. So if we have a helicopter, oh God, that word helicopter. If we have a helicopter and it's got several lrad devices on it, and they're each broadcasting, I don't know, 20 or 30 degree beam down, then you could theoretically, depending upon the height of the helicopter, get a pretty broad coverage. And that way the beams would hit the heads of the audience, and since it is a wide beam, it would cover a wide swath. So you can range these multiple LRADs to have various different coverages based upon the elevation at which you're broadcasting, the direction, and all this stuff. But once again, when you start looking at what signals they're broadcasting, it's often very limited. You get them going from 2.8 kilohertz to 3 kilohertz. So, forget hearing your snares and your piccolos and women screaming and all that. It's just basically used for broadcasting very loud warning signals and very limited speech signals. And in fact, all of these lrad devices are optimized for vocal conversation or messaging delivery. And even the some of the more dynamic of them, which have a frequency range of 1 kilohertz to 5 kilohertz, that's still not going to get you the upper or the lower frequency range of events, of acoustic events. Alright, so now let's take another scenario where, let's go over and look. What do gunshot sounds look like in terms of frequency that makes these lrad devices so improbable to be used? Well, if I drop down here and let's say I'm going to load up one of my favorite, which is a sonic visualizer session of Under. It's not really under the bleachers, it's under the stage. But when I first saw it, I thought it was under the bleachers, so that's stuck. So what I'm doing is pulling up the sonic visualizer session for this recording, which occurs in the approximately in the center area of the stage, but underneath. And it's not on top of the stage, it's underneath. And what I want to bring your attention to is the frequency at which these signals occur. So, on the left, this is a frequency versus time plot. This is what happens when you run that waveform through a fast Fourier transform and you convert it into frequency. And as you can see, there's a lot of different things that occur. This little grouping here is a series or a volley of gunshot sounds. And if we expand it open a bit, we can see that, I'll put that there kind of out of the way, that there's stuff, i.e. signal, all the way from almost up to 17 kilohertz or 17,000 hertz, all the way down to below 100. So no LRAD device that I know of could faithfully reproduce all those sounds. So right away we can go, LRAD not used for this signal, because it doesn't have the frequency response necessary to reproduce the sound. Now in this third panel down here, I've optimized the gain on it so that you can see roughly this separation. And the separation right here is the bottom part are the muzzle blast, and the top part are the supersonic cracks, or the shock wave produced by the supersonic bullet. And as you can see, the supersonic cracks are the higher frequency than these other things. But even in this case, even the muzzle blasts have components a little bit above 1,000 hertz. They're most dominant down here below 1,000 hertz, but they do have components sometimes when they're very strong signals. So if you were using an LRAD device, you would get everything black from, oh golly, even with the best one from, let me draw a line where you would see the signal. The only thing you would see would be the band from about here to about here. And all this other stuff, let's see what happens if I draw black. Yeah, there we go, we can do that. This, I'm going to do a small region of what it would look like if somebody was trying to spoof us with an LRAD device. And this is probably one of the best ones, which has low power at long range. So we would just see this range in there, none of the other stuff. So immediately I see that this is not an LRAD generated signal. And that's all I need to know. There's no LRAD device used. Now, let's talk about where it's at. First I got to get rid of what I was doing. There's a lot of black in there. I don't know how that's going to work out, but anyway. So, where was it and where were the people? If I take an overhead view, and this represents the stage, we'll say the stage here, and this kind of represents a sound box, and there was that walk area out there, and actually the stage was bigger than that. Then this recording would be made right here and kind of down under the stage next into some lattice work. They were actually kind of hidden under it. You could see through this lattice work looking out. So the fact that they were kind of under the stage, that would mean that any LRAD device coming from this direction or down above would not hit them. And the only way they could even remotely get to it would be from these directions. Now this one would be blocked because that catwalk thing was there, so you really would be limited to something over here. But then they're behind the lattice work, which means that again most of the LRAD signal would be blocked. But you just saw the frequency response, so immediately you know that LRAD wasn't used. But these are the limitation type things of LRAD. Let's talk about using multiple LRADs. Let's say we have a 15-degree beam of an LRAD being broadcast from an elevated position so that it hits people's heads, and it can hit multiple people at once so that they can hear it, because after all that would be the intent, is to have people hear it. And using it at a ground level would be essentially worthless, which is why these tanks that roll through with these LRADs on it, just a few feet above people's heads, have a very limited implementation range. So anyway, if we had an LRAD, two LRAD devices, and they each had 15-degree beams, and they were 1,000 foot away, let's say, then one might look like this as a function. And let's say there was another one and it was up here, and it might look like this. Okay. And then there was, you wanted some more coverage, so you have another one that look like that, and that's 3 of them. So the dark areas where nothing is heard regardless would be here, here, and here. In these regions where they overlap, and let's say each one of them was broadcasting a signal that, I don't know how to represent a signal. Let's do a different signal for each one. Let's do, for this one, let's do a square wave. That's the signal being broadcast. For this one, let's do a sine wave of long wavelength. And then for this one over here, let's do a spike. 2 spikes, actually. All right. So then, the people in this one, where you have the square and the spike, would see a signal that kind of looks like this. Okay. The people where it is, actually, did I do that right? I did that wrong, because that one is not the square and the spike, it's the sine and the square. So in that case, the signal would probably look something like this. It would probably look like, it's kind of hard to do, but like that. Okay, because it's the superimposition of this long frequency sine wave and the shorter frequency square wave. And then the region in here would have all 3. So if I were just broadcasting the same sound of gunshots through all of these, this region would have 2 copies of it. This region would have 3. This would have 2 and 2. And so that would be the problem when you have these multiple overlapping LRADs. And if they weren't overlapping, then you'd have all these black areas. So once again, it would become very, very obvious when you look at those signals that I was showing you that there were multiple LRAD devices being used. And that's without measuring time of arrival. Time of arrival is a whole nother ball game, because as we know, sound travels at a little over 1,000 feet per second there in Vegas that evening, probably around 11:58. And if I have an lrad device operating on the left side of the venue, have one right, yeah, right. That was not my left, that was my right. We'll call that east. And I have another one operating over here by the stage, pointing towards the center. Then picking a location. If we pick a location that was close to the stage, then the time of arrival of the sound from this lrad is short. And that's when it would hear it. If I pick a position over here, the time of arrival, which would be receiving the signal from that device, is long. And if I were to pick a spot that was in between the two, well, let's just pick a spot here and presume they don't overlap. Up here, the time of arrival is going to be that path length. And so if each lrad device was broadcasting the same signal, the time of arrival of that signal would vary proportional to the distance from the lrad to the observer, and they would all be different. That is, if this was 1,000 feet, and this was 1,000 feet, which in this picture they're not. Now that's a bad example. Just forget that. Okay, back to the way I drew it originally. So the time of arrival is measuring the time between when the lrad broadcasts and when you hear it. Okay. So each of these locations would have a different time of arrival, which is to be expected. The distance divided by the speed of sound, that would be okay. But to if we well, let's pick yellow, I guess. If we have a sound here and we want to make believe it's a single gunshot, then this signal gives you one time delay range, and this signal gives you another time delay range, which means it would appear as though the shooter were in two locations at once, or that there were two shooters. So that represents a problem. There can only be one sound for each round from a muzzle blast, for example. And that was stated poorly. If you hear two muzzle blasts per round, which is a better way of stating, if you hear two muzzle blasts per round and one is not a reflection or reverberation type effect, you got a problem. And that's what having multiple LRADs would do. Even if they could faithfully reproduce the frequency range, which they can't. And I don't know about you, but setting these things up ahead of time, I think would be a nightmare. How would you predict? Where would you set them up for out there in the dirt parking lots? Where would you set them up for over there at Oasis Apartments or up at the Excalibur? Do you have them set up all over town because the sounds were heard all over town? Or do you think that these LRADs have enough distance built into them to do it? So, it's just a preposterous situation. There's just too many technical difficulties to overcome. The expense would be outrageously exorbitant, and quite honestly, there's no technology I know of that can do it. Period. So forget going with LRAD theories, and anytime somebody says it was an LRAD device, ask them which LRAD device it was used that could produce, 200 hertz to 20 kilohertz. And that's all you have to do. Ask them how you got the LRAD signal underneath something or behind something. Ask them how there was only one muzzle sound when you have to have multiple devices to simulate to cover the whole area. These are all simple things. In addition to that, LRADs are very good at focusing signals and making them loud. And that's their whole design, which is to overcome the problem of sound decaying at distance. And so even the loudness of the sounds is going to be contrary to what you would expect from a normal gunshot acoustic phenomena. I think I've covered part 2 of this adequately enough. I'm sure there'll be some questions. I love questions. I know of no configuration of LRAD devices. I know of no product that would be adequate and up to the task. Period. They could, if you could find such a device, it might be able to do the might be able to faithfully reproduce one device anyway, timing of some muzzle blast, but it could not do the supersonic cracks, because the supersonic cracks are created at the speed of the bullet. And if you're using a device which operates at the speed of sound, it's kind of hard to beat the speed of sound. All right, that's enough for that. We'll move on to the next topic.